For problem number 5, we did this in class, but I want to go through it with you in this video just in case it was moving too fast and you need a little bit more instruction or more review. The key thing that we want to look at here is that it is a conducting sphere. The net charge is Q, but what we know about conductors is that the charges are free to move, which in this scenario, the charge, which is positive, is going to move on the very outside surface of our conductor. And this is only for conducting spheres. We also learned conceptually that the electric field inside conductors is 0, but this will give us another way of solving that, which if we create our Gaussian surfaces, we're trying to derive the electric field at a distance r less than a. So if I have a Gaussian sphere, and usually you use dots to represent that, the radius by convention for Gaussian objects is a radius of lowercase r. For the electric field greater than a, I'm going to create another Gaussian sphere that is greater, so at this position, and it's still a radius r. Now remember that r is arbitrary. It can be small if we're analyzing the inside of a sphere, or it can be large if we're analyzing the outside. So it is a changing variable, but when we plug it into our Gauss's law equation, we plug it in knowing that that is an arbitrary value. So let's start with our Gauss's law. It is the enclosed integral of E dot dA is equal to Q enclosed over epsilon naught. I love the video where it talks about how the left side, even though it looks complicated, is easy. Because for both A and B, we can solve for the left side and it doesn't change. Whereas when I'm analyzing the answer to A and B, the right side, which would be the Q enclosed, is what changes our answer. So when we are enclosing a surface, we are taking pieces of the surface area until we have covered the entire surface area of this sphere. And so even though this looks like a complicated integral, you're just going from 0 to the full surface of a sphere. And again, even though our r is arbitrary, we're going to plug it into our expression. And when we integrate the dA, we get E dot A. And we go from 4 pi r squared to 0, and that just gives me E times 4 pi r squared equals Q enclosed over epsilon naught. Now I'm solving for electric field, so I am going to isolate the E right off the bat and divide that 4 pi r squared to the denominator, but I'm rewriting it so you can see that 4 pi epsilon naught, which we've seen many times before, is equal to K. So in the answer key, it'll show you this answer as 4 pi epsilon naught in the denominator, but we can also write it as K Q enclosed over r squared, which is the expression that we use for a point charge. Now, when we are looking at the enclosed Q for r less than a, that's this enclosed Q right here. Because we know it's a conductor, and because we know that conductors allow charges to flow, all of those positive charges are trying to get as far away from each other as they can, which means that there are no net charges inside of the sphere. And therefore, our answer for the Q enclosed is going to be 0. 0. So for this first part, The electric field is equal to K times 0 over R squared, which is just 0 newtons per coulomb. When we are doing the second part, which is when R is greater than A, we now can see that we actually have a charge enclosed. In fact, that charge enclosed is Q. Now, I'm going to still look at this equation because, again, even though my R in my 4 pi R squared area is bigger, it's an arbitrary value. So I can still leave it in this term, but now I have to think about what is my charge enclosed. It's not 0 when it's greater than A. It's actually big Q. So I plug that into my expression. This is for part B. Electric field is KQ over R squared. And as I stated, when you're looking at a charged sphere and you are outside of that sphere, you can treat it as a point charge. And this is our equation that we learned for electric fields of a point charge. Now on our diagram, we are going to draw that electric field when it is inside of the circle or between A. We can express it as 0 on our graph. Then when it's greater than A, we can see that it has an inverse squared proportion because there's that R squared in the denominator. So I'm going to jump up to, and this is going to be KQ over R squared. And then I am going to, as R increases, approach 0. Same on the other side. Jump up and then decrease and approach 0 on the left. So our graph looks like this for the electric field radius graph.